Swayam Prabha. Digital India. Educated India.
Hello and welcome back. In this video we will look at boosting, which is another technique for improving the performance of decision trees. Most of the slides, graphics and illustrations were provided by Intel software, and the content is inspired by the textbook Elements of Statistical Learning. Okay, so we saw that in the last lecture bagging improves performance primarily by reducing the variance, and that is accomplished by training multiple decision trees over bootstrapped samples of your data. Okay. And the output is basically the average of all the decision trees when you are looking at a classification problem, or you take a majority vote. If the output is the average from all the trees when you are looking at a regression problem, or you take a majority vote if you are looking at classification problems. So, in this lecture we will look at boosting, which is an alternative to bagging and also improves prediction accuracy. Okay. Okay, so we will take a brief overview of boosting just to get an understanding of the algorithm. And one of the classifiers used in boosting is a decision stump. It is basically a tree with it's a classification tree with one node, and it splits the data space into two. These decision stumps are referred to as base learners, and if you want for boosting or bagging, we can use these stumps or more complicated decision trees. So, as I mentioned earlier, the building block for boosting is decision stump primarily, and it has one node. So, if you look at a particular data set which has temperature as one of its features, so we can split the feature space into two at this particular node based on a threshold on the temperature. So, this is just an illustration of how the decision space is split into two, and this is your classification boundary. So, all the data elements, data points to the right of the classification boundary or belong to one node, and to the left to the other. Okay. So, we will use a collection of these to perform boosting. Let us see how that is done. Okay. So, brief overview. So, we create an initial decision stump based on one of the features to split the data space into two. Okay. So, just for the sake of illustration here, we are just showing a 2D plot. Of course, we know that an input data can have multiple features. So, we are looking at just one feature, and maybe here this is a visualization of a couple of features. Okay. So, based on the splitting by the decision stump, then we have two classes. So, again we are looking at a binary classification problem where the output is either -1 or 1. Okay. So, we have this decision boundary, and we have correct classification of the red data points to the left, and the correct classification of the blue data points to the right. These red crosses on the right are basically misclassifications, right. So, then what we do is we adjust the weights of those points. So, we assign some data weighting to those points when we calculate the loss function for the decision stump. We do a further classification after assigning weights. So, think of assigning weights as, if you take a simple least squares cost function, you will assign a higher cost to these data points compared to the others, or if in fact you can even suppress or make the contribution of these data points minimal compared to, that is, the data points that have been classified accurately to a minimum, and you can assign higher weights to, or higher weights in the sense higher loss for misclassification loss to the data points that have been misclassified by the previous decision stump. So, then we have these reweighted data points which you classify again to get a new classification boundary. In this case, again all the red points have been classified correctly, while there are a few misclassifications for the blue data points. So, and then one more time we do the reweighting and get a new classification boundary here. So, the output of boosting is basically the sum of all these boundaries of all these classifiers. So, each one of these we will call this G1x, G2x, okay. So, each of these classifiers G1, G2, G3 provide you a classification boundary, and based on that classification boundary you have a classification as -1 or 1. The points that are misclassified are accorded higher weights for the successive classifier. So, most of the time these are decision stumps, that is what we saw earlier, decision stumps, right. So, the next G2 is a decision stump which takes the same data as input, but the data points are which have been misclassified by the previous decision stump are given a higher weighting. Finally, the classifier that you use in the end is basically the summation of all the individual classifiers. Okay. So, and in order to improve this, since they are prone to overfit, you typically have a weighting factor here alpha, that is I will call it. So, this will be different for each one of them. So, we will call this alpha 1, alpha 2, so on and so forth to get you a final decision boundary. Okay. So, the result of boosting is a weighted sum of all classifiers, and successive classifiers are weighted according to some scheme which we will see in the later slides. Okay. Okay, the AdaBoost algorithm, which is one of the boosting algorithms, adaptive boosting algorithm, it is a very popular boosting algorithm. We will look at it in the context of a 2 class problem, where the output of the classifier is -1 or 1, is basically the so it is a binary classifier, and the resulting classifier is the weighted sum of individual classifiers. We have capital M classifiers, each of them can be decision stump. So, we have a weighted sum of these classifiers as the output. So, the sign of the weighted sum of these classifiers is the output. Okay. That is the problem we are trying to solve. So, how does the AdaBoost algorithm progress? So, initialize data weights to 1 over n. So, when we start out, we assign the same weighting 1 over n, where n is the total number of data points, to each of the individual data points xi. Okay. And for M classifiers, capital M classifiers, for each iteration, you fit a classifier to the data xi using the weights wi. So, in the first iteration the weights are just 1 over n, they are all the same. Okay. So, and then we compute this term error, this error term after the classification, which is given by this expression. So, this is nothing but the weighted error term. So, if you look at this this particular expression here, this is nothing but the number of samples that have been misclassified. So, GM of xi is the output of the mth classifier, and yi is the ground truth, and we are just counting, I is the indicator function. So, we are just counting the number of samples xi that have been misclassified by this GM. Okay. So, the error that we calculate for this classifier in the mth iteration is the weighted error based on the weights, which for the first iteration is 1 over n. Okay. So, how do we update the weights? That is what we will see. We also have to compute these alpha m, which are the weightings for the individual classifiers. So, we can calculate alpha m using this expression. Okay. And once we have calculated the alpha m, then we can go ahead and update the weights. The weights for the next iteration are given by this expression, where again it is a weights from the previous iteration times this exponential factor. Okay. So, this is the loop which is performed m times. In the end, we output the classifier as the weighted sum of the individual classifiers. Okay. So, this is just the algorithmic summary for what we saw earlier in a very in illustrative form. So, in every iteration you you fit your data to a what is called a weak learner or a weak classifier. Okay. and you look at all the data points that have been misclassified, and you assign higher weights to those data points. So, that is what this step does. So, you assign higher weights to those data points, and then you take those data points, all the data points including the ones that have been misclassified, but then with higher weighting, and you perform one more, and you fit that data again using another classification tree or some other classifier, and you repeat that as many times as the number of classifiers that you want to use. Okay. Again, it is easy to see that since this m is another seems like a free parameter, it can most easily overfit. So, that is one of the reasons why we iteratively calculate the weightings, so that the learning up happens very slowly. Okay. So, over a large number of classifiers, you will come to the weighted linear sum would give you a good classification accuracy. The point to note is that these individual GIs or GMs can be weak learners, in the sense they perform as well or maybe poorly than random classification. So, if you accumulate all of them over capital M iterations, you can get to a very high performing classifier, right. So, where does this idea come from? So, this is basically has roots in this additive modeling. So, where we have this particular model where our classifier is nothing but a linear combination of multiple classifiers. So, each of these GM can be a decision stump as we saw earlier, or they can also be regular classification trees. Okay. So, now the problem is when we have a cost function, you can see that the individual classifiers will have their own parameters, and we also have to estimate these beta m's. Okay. So, how do we go about doing that? So, when then that is accomplished using this forward stage wise additive modeling. So, let us have a look at that. So, we start off with a function initialized to 0, then for m steps, so as many classifiers as we have, optimize the parameters of the mth basis function or classifier. So, the way it is called basis function is that, so if you might all be familiar with the linear regression class that you have been through. So, we can, let us say if you are doing regression, let us say y we can model as w naught plus 1 x, in this case plus x to the m, right, capital M. So, this is one of the models that we have that we have seen in linear regression. So, we can consider each of these x square, x to the m, these polynomials as the basis functions. So, we can write it in this way. So, here these correspond to the g m of x. Okay. So, we can think of each of these classifiers as some basis function, and we are trying to iteratively estimate the parameters corresponding to each of them, and also the weighting that we have to assign. So, basically these weights, or in this case these x are very this is a very simple polynomial. So, we can assign, for instance, instead of x we can use some basis spline functions. Okay, they will have multiple parameters that we will have to determine. Okay. Now, when we put this in the cost function, it becomes very difficult to determine. So, what we go about doing is in every iteration we only estimate that particular GM. So, in the mth iteration we will only estimate GM of x, okay, without changing the parameters of the first m minus 1 classifiers that we have built. Okay. So, for every iteration optimize parameters of the mth basis function. Okay. So, which is basically given by this formula here. So, argmin with respect to the beta and gamma m, L is the loss function for one data point. So, it is summed over n data points. So, L is a function of course, your L takes as input your ground truth yi, your classifier from the previous iteration, and this is the classifier that we want to estimate. Okay. So, the beta and g are what we have to figure out in this iteration when we make no changes to the parameters involved in the classifiers and the beta from the previous iterations. So, once you have done that, then we update the classifier as by adding with an appropriate weight is the basis for the AdaBoost algorithm that we have seen. So, in this case the loss function we have not specified exactly what it is. So, we can actually look at a very simple loss function. Let us say we are looking at y minus I will just call it gm of x squared, which is your least squares cost function. So, based on this L is just that, which we can write it as, I am just going to use x I am going to do it for one data point, right, because the sum of for all of them. So, which is y I minus g m minus 1 of x I minus beta g of x I squared. So, we have developed a classifier till the m minus 1th iteration, right, and we I have just substituted this expression here, and we have, instead of gm of x y we have just used this expression g of m minus 1 x plus beta m g of x. So, this is the cost function that we are optimizing if you use a least squares cost function. Now, we can easily see that this is nothing but the residual from the previous iteration. So, here we can just call it r I minus beta g of x I square. Okay. So, if you use a least squares cost function, what you will end up doing is you will fit a particular regression algorithm to machine learning algorithm to it, let us say a regression tree. So, you will fit a regression tree to your data, and then you will calculate the residual. So, for every xi you will get an output and you subtract that from the ground truth. So, you will have residuals, and then in the next iteration you will take those residuals and fit them with your input data. Okay. So, that is the that is how it progresses if you use a least squares cost function. Now, instead of a least squares cost function, if you use an exponential cost function, what you end up is getting AdaBoost. That is what we will see now. The AdaBoost loss function or the algorithm that we saw for AdaBoost comes from using an exponential loss functions, and the basis functions or the weak learners or the individual classifiers, these can be decision trees or stumps. So, remember previously we saw this L of y comma g of x. I am omitting the subscripts I. We saw that as y minus g of x squared. This is what we used as an example in the previous slide. So, instead of that we have an exponential y minus y times g of x. Okay. So, this product for a classification problem is often referred to as a margin, right. So, we can easily see that, let us say your output is so your category is minus 1, and let us say your classifiers also inputs minus 1, then it is greater than 0, right. Let us say your category is 1 and your classifier also outputs 1, then it is again greater than 0. So, for all positive values of this product you have correct classification, and all negative values you have a misclassification. So, that is the margin, or I can think of it as the distance from the decision boundary is what we look at. So, when you introduce this exponential function as the loss function in order to solve your additive model, again to recall we saw that for this AdaBoost comes under this additive modeling. So, we wanted to get to a classifier which is the sum of individual classifiers. Okay. Right, this is what we sought out, and we wanted to optimize an appropriate cost function to estimate each one of them. Now, if you want to do it the right way, then you would eventually will have a loss function that will try to estimate all of the parameters of Gm and beta m in one shot by optimizing a cost function, but that becomes very complicated. Let us say capital M is, let us say 100 weak learners, then there are 100 sets of parameters for each one of the GMs here, okay, or each in this case decision tree. So, you might wonder what are the parameters for a decision tree. The parameters are denoted by gamma, and they are basically the nodes and the features that you split on, okay. So, that you have to estimate for every tree that you fit. So, to alleviate this problem, we have the additive stage wise modeling, wherein we initially estimate, we do m iteration, capital M iterations, where we start off with one decision tree, okay. Typically in these models a decision tree, which has one decision tree or a decision stump, and you estimate that the parameters of the decision tree, in this case how you grow it, and the nodes and the features, and successfully update by so if you have let us say small m iterations, you do not change the parameters of the first m minus 1 iteration, but only consider the parameters of the mth iteration, right, only update the parameters corresponding to the mth iteration. So, that is this stage wise modeling helps to solve this problem. So, this is the easier way to, so if you will have a loss function which takes as input the y, ideally it will take as input the y and your model, right. So, then you will estimate all of the parameters for all of the individual decision trees for the weak learners in one shot, but this is a difficult problem to solve. So, that is why we saw that we take as input of course your y's, this is the ground truth, and we have a since it is an additive model, we quoted g of m minus 1 x and plus some beta times g of x, and we do not touch any of the parameters here, but only estimate the parameters corresponding to this, okay. So, that is the idea behind using this additive stage wise modeling, okay. So, for if you use an exponential loss function, so this loss function, if it is an exponential loss function, exponentially of minus y g x, then we end up with the ADA boost algorithm. We will just take a brief look at the loss function itself. So, I am going to erase this so that you can clearly see the formulas involved. So, the problem that we will end up solving if we use a exponential model is this argmin of this loss function, because all of the terms are in the exponent, right, and you realize that since we saw earlier that these the parameters here are not at all affected by this optimization problem, because we will only be optimizing the parameters of g, in this case this gamma and beta at that particular iteration. So, we can write this as, replace this by a weight, okay. So, this is the loss function that we end up optimizing for the ADA boost algorithm. So, again we saw some of the update steps there. When I outlined the algorithm, we can calculate the error rate m. From there we derived an alpha, right, which is the, of course, which is related to actually beta that we see here. In addition, we also did a weight update. So, the weights every iteration are updated, right, times some factor, okay. So, all of these can be derived by from first principle using these two expressions. All you have to do is optimize for gamma. So, in this case we are optimizing for beta m and gamma m, which is gamma m are the parameters of your decision tree. So, you figure out the best decision tree by optimizing the misclassification rate or minimizing the misclassification rate, and then once you hold that, once you fix that, then we can optimize for beta, which is which can be done by taking a derivative of this loss function with respect to beta, setting it to 0 and then plugging in the optimal decision tree. These weights, the update rule for these weights, the estimate for beta extra can be obtained by just optimizing this loss function. Even analytical expressions can be obtained. So, this is the basis for the ADA boost algorithm. So, we will look at just to have a look at understanding what this algorithm actually does. So, we look at this red curve here. So, it is a 0 1 loss. So, let us say we have a binary classifier which classifies your output as 1 or minus 1. So, what we ideally want to do is to assign 0 weights to all the correctly assigned data points and a maximum weight of 1 to all the misclassified data points, and then move on to fit it with another regression tree or a classification tree depending on the problem. Okay. But this kind of loss function is difficult to optimize. So, that sense it is replaced by this exponential loss function, that is what ADA boost does. Okay. So, the exponential loss function as we saw is the e raised to minus margin, where margin is where this makes the ADA boost more sensitive to outliers than other types of boosting. Okay. The theoretical loss function, even though is very intuitive, we can see that here. So, ideally what we are trying to do is we take a data set, let us say 100 data points. In the ideal case is what we do 100x data points. Let us say some 30 of them are classified correctly and some 70 of them are misclassified. Okay. Then in the next step, so this is G1, and G2 what you will do is you will take 70 and then fit another classifier. Okay. But this is this problem, even though it looks very appealing, does not give good results because it is a difficult problem to optimize. On the other hand, having a exponentially decreasing loss function instead of this step loss function helps improve your fitting. Okay. So, in the next class we will look at a further modification to this called gradient boosting. So, the procedure we outlined here works very well for the exponential loss function. However, gradient boosting techniques are good for pretty much every kind of loss function that you can come up with. So, it is a very generalized procedure for doing boosting, and it is also one of the apparently to many sources one of the more popular techniques to win these Kaggle competitions. So, we will look at those in the next video. So, the ADA boost loss function is an exponential loss function, and the basis functions as we had mentioned earlier are nothing the individual classifiers or the decision trees or the stumps. Okay. So, recall that in the previous slide we looked at a least squares function, right, wherein we did y minus g of x squared, right, and this additive modeling proceeds, or the stage wise additive modeling proceeds by trying to optimize, trying to estimate this. So, we want to get this classifier which is nothing but, and we can use either alpha or beta, but just use. So, if you have a loss function, it will take as input your ground truths and your model, which is what we did, right, and ideally we would end up estimating all the parameters of each one of these individual classifiers as well as the weighting factors for each of those classifiers in one shot. But when you are using, let us say, decision trees, this becomes a slightly difficult problem to solve. So, we solve this problem in a stage wise manner. So, that is why we saw earlier that we ended up with your initially we start off with this model, that is your G x plus okay. So, this is the model. Here what it means is that we will not touch the parameters up to in this model are not affected at all in the when you are optimizing this loss function. You are only optimizing for beta m and this g at this particular step n, particular stage m. Okay. And so, we saw how this works for the least squares cost function, and instead of the least squares cost function, if you use an exponential loss, so what does it look like, right. So, this is the you have so this L is given by, so this function where this particular term y times g of x is the margin. Okay. So, you can think of it as the distance of the data point from the classifier. Farther away it is, the worse the classification, you can think of it that way. Or if for a binary classification talks, you see that y times g of x is always positive, right, because g of x is the output of the classifier, then your classes are -1 and 1. So, y times g of x will always be positive when your classifier is right and negative when it is not. Okay. So, we have, instead of the least squares, we saw it like this, we have put in the exponential loss function. Okay. And in the mth stage, we will not modify the parameters of these class g m minus 1, but rather only focus on estimating beta and gamma here. So, for the in the case of regression trees or classification trees, gamma represents the nodes and the features used in the split. Okay. So, in every stage you will estimate one, you will figure out one decision tree or stump, and you will add that to the classifier that you have already estimated so far till the m minus 1th stage, right. So, since this is not involved anywhere in the optimization, we can interpret this as a weight. Okay. If you recall the you can go back and look at the ADA boost algorithm that we outlined, then we had this quantities error, and from where we calculated alpha m as well as the update to the weights. This alpha and the beta are related. Okay. So, alpha turns out to be, I think, beta over 2. So, how do we, so the estimates can be derived analytically by fixing beta and estimating g, which is nothing but the best classification tree you can get. So, you get the best classification tree by minimizing the misclassification rate. Once you have figured that out, then we can then fix that and then take the derivative of this expression with respect to beta, and we can do further analysis. Okay. So, if we do that, then we get all the update rules that we saw earlier. So, that is the basis of the ADA boost algorithm. It starts from this additive model right here. Okay. So, it is like a linear basis function model. Okay. So, gm of x or basis functions. In this case, we have used decision trees, we can use other structures also if possible, and in every step we successively improve the classification or the prediction accuracy. Of course, so far we have only looked at the binary classification problems, it is also applicable to multiple classes. And another thing is that we have only looked at this discrete ADA boost, wherein we assume that our classifier returns -1 or 1. We can modify this even in the case when our classifier returns probability values mapped between 0 and 1 corresponding to classes -1 and 1. Okay. These can also be done. For the sake of illustration, we have only looked at the binary classifiers.